All right, welcome to ECE 6465. First of all, let's go through some logistics of this course. So here the title is Memory Device Technologies and Applications, and the course has 3 credits, and we are meeting here today, Tuesday, and also Thursday in a week, and from 12:30 to 1:45 in this classroom. So this is fully in person. Even though we record the lectures, we do not offer, the hybrid mode. So the recorded lectures will be uploaded to the YouTube after the class, just in case you want to review some of the discussions. So here, all the course materials will be uploaded to the Canvas. If you are enrolled in this course, you should have access to the Canvas for the ECE 6465. All the lecture slides, homework assignments will be posted on Canvas. And if you want to learn something in advance or ahead of time, then we do have a recorded lecture series from the past semester, that is for 2021. So in this YouTube link, if you want to learn something in advance. But here in this semester, we are going to update some of the lecture slides. So you will tell there are some new contents in this semester's material. And here are some details about myself. And here my office is in the Pettit building, just across this bridge. And the best way to reach me is to send me an email. And my office hour will be Thursday, 10 a.m. to 11 a.m. in my office. And more background about myself. I got my PhD from Stanford in 2013. And after that, I spent a few years at Arizona State University. And then I started my teaching in this course. So about like 10 or 11 years ago. So after that, I moved to Georgia Tech. That was 2018, and got promoted to the Dean's Professor this year, and also elevated to the IEEE Fellow for contributions to the non-volatile memories and in-memory computing. So basically, the memory is, my expertise. So that's why I'm offering this class to the departments. So if you want to understand more about our research, you are welcome to visit our lab website here. So here are the course objectives. So as part of this course, you will learn the knowledge about the memory bit cell. That means a single memory cell, about its stability, variability, and reliability. Of course, we are going to cover different kinds of memories, but no matter which memory technology we talk about, you will start from a single bit memory cell. We call it a bit cell. And then we will talk about the stability, reliability, and variability issues. And then after you understand the bit cell, then we're going to talk about the array, because memories needs to be organized into an array to be functional. So then we will learn the bit line, word line, and decoder, and so on. So we need those peripheral circuits to operate the memory array with appropriate timing, like read or write timing and biases for those voltages to apply to the word line or the bit line. And then we will also emphasize the scaling trend of the memory technologies, no matter it's mainstream industry technology or the emerging memory technologies that are actively being researched by the academia or the industry pathfinding groups. So we will understand how to scale the memory technologies and what are the challenges in the scaling. So again, this is a graduate level, cutting edge, technology-oriented class. And we will emphasize industry trends So this is very different from many other standard textbook-based course. This one is more practical and industry-driven. So as part of the learning process, you are expected to read some of the literatures, that means papers, as part of your homework assignments. So you will understand the industry trends. And the prerequisites. So if you are coming from Georgia Tech, then the undergraduate level semiconductor device and digital circuit courses are required, like 30/30 or 30/40, or equivalent if you did your undergrad in other institutions. So basically the undergrad level semiconductor device physics and then digital VLSI courses are required. And then graduate level, the same topic. So you are encouraged to take other, semiconductor device and digital system, VLSI system courses at Georgia Tech, like 64/50 or 61/30. So those are not required, but just suggested. So textbook, no official textbook, but like 2 years ago, actually 3 years ago, during the pandemic, I spent quite some time to write a kind of reference book for this course. And it's titled Semiconductor Memory Devices and Circuits. You don't need to purchase this because it's available through Georgia Tech Library. And I actually tried. You can download from Georgia Tech Library, the PDF. So any questions so far? All good? All right, so then this comes to the what you may care about. So assignments and grading. So the homework will consist of 5 problem sets, each like 10% of the weighted assignment. So that means homework in total 50% of the total grades. And in the homework, you may need to use some software tools like MATLAB or some equivalent tools to solve some problems. And submit your homework digitally through the Canvas. So basically scan your paper and then upload through the Canvas. We don't take the paper homework submission. And then we will have the midterm exam and the final exam. Each is like 25%. So the exam will be closed book, closed lecture notes, but you are allowed to bring one cheat sheet, like the A4 paper size, and you do need a calculator for the exam. So exam, if it's midterm, then it's in this classroom, and then for the regular lecture, like 1 hour and 15 minutes lecture time. And if it's a final exam, then we will follow the registrar's, the schedule, and we don't know that, or maybe it's already posted. I didn't check. You can check. Okay. So again, close book, close lecture notes, and then you can bring the cheat sheet and the calculator. So the final letter grades will be based on a curve using all the graded components. And here is just an expected grade distribution. Okay, I have to emphasize this is subject to change. This is just some example from the past semester. It may apply to this semester or may not, depending on how well or how bad you perform in the class, in the exam. Okay, but here you can get some ideas what you may expect. So any questions? Okay. Clear? Okay, so additional policies. So all the homework, assignments due by the deadline. And if you are submitting late, like within 24 hours, then your score will be multiplied by a factor like 80%. So if your score is like 90, and then you will have additional penalty. That means 90 times 0.8, then you will get 72. So if it's between 24 and 48 hours late, then the factor will be 50. And beyond 2 days, 48 hours, then we don't accept. Then you will get 0 for that homework. So if you have any questions regarding the grading of the homework or exam, you must be addressed or ask me within 1 week after the homework or exam is returned to you. So this is to avoid the situation like at the end of semester, then you come back to my office and ask like 2 more points in your homework 1. Then this is not allowed. If you have any questions, ask right away. And then please refer to the syllabus regarding other issues like the academic integrity and accommodation for students with disability and so on. So I won't repeat those here. And then the syllabus is already uploaded to Canvas. You can refer to that. Here is an outline of the topics to be covered in this semester. So we will start from some overview of the memory subsystem, and then we will review some of the CMOS scaling trend. So this is again to introduce the industry scaling trend. And then we will dive into individual memory technologies, start from the SRAM. And then we will talk about the topics like the basic cell, 6-transistor cell operation, and then the stability, scaling, and the layout, and also the variability, reliability issues. And also we will talk about the recent trends. So here are some things that I added for this semester. So because 3 years ago, I only thought about FinFET-based design. But you know, the industry is evolving very fast in this space. So I like to introduce new topics for the leading edge node. That means 3 nanometer, 2 nanometer, 1 nanometer, and beyond. Include the transistors based on the stack nanosheet and backside power delivery, which is important to maintain the scalability of the SRAM for the future technology nodes. And also, we will talk about the DRAM and basic 1 transistor, 1 capacitor cell operation. And then we will talk about the fabrication of the DRAM process, and then the layout. And then we will also introduce the recent trends, because this is a very hot topic. The HBM, high bandwidth memory, which is based on 3D stacked 2D DRAMs through the bonding process, like the TSV through silicon via, and then the micro bump. And then I will introduce the future scaling possibility for the DRAM, that is the monolithic 3D DRAM, which is still under the research by the academia and also the industry pathfinding group. And also, if time permits, I will introduce some ideas about embedded DRAM, which could be integrated with your logic chip. And then flash memory. First, the device physics, and then the LAN and NOR architecture, and then the reliability scaling issues for the flash, and the recent trend, 3D vertical LAN flash. So actually, I look at the past 3 years, not many new ideas on the 3D NAND flash, except that the 3D NAND become higher and higher. Then no other, fundamental technology breakthrough in the flash. So we won't see too much updates in the lecture slides in this space. But anyway, industry still keep scaling, but just simply add more and more layers. Of course, there are many challenges in doing that. we will talk about what are the challenges there. So after we go through all the main memory technologies like SRAM, DRAM, Flash, then we will talk about some emerging technologies. And some of those emerging technologies have already been commercialized by the industry, but still some of them are still, under research. But anyway, we will cover those topics like the cross-point array architecture and RRAM resistive random access memory, phase change memory, PCM, MRAM, magnetic random access memory, and ferroelectric memories. And my research group actually actively work on some of those memory technologies, these emerging memories. So we will show you some of those latest research progress in those domains. And finally, we will talk about the memory array design. There are some circuit level techniques on the peripheral circuits, especially the sense amplifier, which is very important to detect the data from the memory array. And we will introduce some bank level simulators for you to practice how to design the memory array from the architecture and organization point of view. And then the final topic, we will talk about the new applications, which is in-memory computing. This is also a hot topic for research because people think this is a good way to accelerate the AI algorithms on chip. So we are going to introduce some of those concepts for the in-memory computing as well. And here, this is a tentative schedule. Again, I'd like to point out, this is subject to change depending on the pace and progress, or maybe my travel schedule, because I have many other responsibilities to the community and also the sponsor companies. So I may have to fly out to meet some of those folks. But anyway, this is a tentative schedule right now. And the midterm is somewhere here. And then the final exam is in the final exam week. And we have the homework, 5 homework. I think that's pretty much what I want to share at this moment for the logistics. So any questions? Oh, this is a very shy audience. So if you have any questions, feel free, okay? All right, so then let me stop here for the logistics. I will.